talk molto interessante di sistema, appunto, sulla costruzione dei sistemi sicuri e affidabili. Talk in inglese, vero Federico?
Sì, grazie.
Il floor è tuo, come si dice. Vai.
Grazie mille. Passo all'inglese. So hi everyone, I'm Federico. In this talk, I will talk about how to build secure and reliable systems. And I think security and reliability are fundamental aspects of a trustworthy system. And I think we should think about those aspects throughout the whole product lifecycle. And even though security and reliability need to be central points in the system architecture, it's also a hard choice to figure out how much we want to invest in improving security and reliability, and what is like our target. I think that trying to reach 100% reliability or 100% security is not so effective because it's basically impossible to achieve. And for example, in the case of reliability, especially, it's sometimes more than what users would even notice. Like if our system, let's say, we work very hard to and spend a lot of resources to make it available, like a very high percentage of the time. For example, we only offer 1 second per year of downtime, let's say, but our users have a laptop or a connectivity that has way worse performance than that, then users might not even appreciate all the effort that we put into the system. So it's very important, in my opinion, to quantify risks and implement mitigations to make sure that the residual risk would match what the business can accept. So this talk is actually based on a book, which is also called Building Secure and Reliable Systems, that was published in March 2020. The authors are colleagues of mine, and I also contributed to the book. So later I will give you some pointers on how to reach this book, which is, by the way, available for free online. So as I said, I'm Federico. Some people might know me as Fox in the Italian community, and you can find me on Twitter at FoxTN. I'm a site reliability engineer at Google. So in the words of the founder of Site Reliability, who is Ben Traynor, site reliability engineering is when you take software engineers and you ask them to work on operations. So we try to use software engineering patterns to automate systems and make sure that we can reach high reliability that is adequate for the needs of our users. And we work hard to make our users happy so that they can use our systems. In the past, so I've been at Google for about 5 years. Now I work in the Munich office. In the past, I worked for quite some time on Beyondcorp, which is an effort that started at Google around 2011 or 2010 for improving the security of the corporate network. The main idea behind Beyondcorp is that we shouldn't give access to people based on which network they are coming from. So back in the day, we used to have a VPN that employees could use to connect to the corporate network, and from there, then get access to internal applications. But this has the problem that communications are not authenticated or authorized properly. Like you have a very coarse authorization system. So with Beyondcorp, we changed this model and we moved all internal applications reachable from the internet. So it's very easy to work from anywhere, but with a very strong layer of authentication and authorization that also provides auditing. Also, I worked on our continuous integration, continuous delivery systems. And as I said, I'm a contributor of the Building Secure and Reliable Systems book. I'm interested in security, even though it's not my main job. And I play Capture the Flag competitions, which are security competitions for players to learn about security and get challenged by interesting tasks. And I also organized the Google Capture the Flag together with many other colleagues. And this is I think, a very nice event if you want to get into security. and try to challenge yourself. And we do it every year. So as I said before, it's very hard to balance security and reliability and to provide these two features together. But I think they are very fundamental for a trustworthy system. We shouldn't really try to strive for one or the other. I would argue that we need both, especially if our system is something that our users need, and we handle user data or other sensitive information. And also, if you think at the CIA model, the confidentiality, integrity, and availability, the availability is a very important part of this triad. And it might be like a bit of antiquated model, maybe, to think about security, but still this reflects also the reliability aspects. The problem is that building a system that is secure and reliable is non-trivial. To give you some context on that, we can go back to September 2012, when at Google there was a wide announcement that the password for Wi-Fi networks on the bus system that is available in the Bay Area was changed. So in the Bay Area, employees can get a bus provided by the company to go to the office. And they have Wi-Fi on that, so work if they want, or I don't know, do whatever they want. The password was changed. So people, what they ended up doing was just connect to our password storage system and check what's the new password and input it into their laptop and connect to the Wi-Fi. So this caused this email that was like very innocuous caused a very big spike in traffic that actually broke the password management system, which was developed many years earlier, and it was not really thought to be used by the whole company. It was mostly for system administrators back in the day to handle like some small amount of passwords. So like the system was also thought to be reliable, but there was a load balancer. So the primary replica failed because of the spike. All the traffic went directed to the secondary replica, which also failed because there was still the spike of traffic. Luckily, or by design, there was an engineer that was on call, and this engineer was paged. But unfortunately, there was no big experience in the team handling this kind of failures because the on-call rotation was best effort, because this was not like a very production critical service. And also in the previous 5 years, it never experienced an outage. So the engineer also like didn't have that much experience, and there was also not the experience didn't build up in the team either. So what the engineer did was to restart the service, but the restart failed, and this is because the password storage system uses a hardware security module with a smart card to only decrypt passwords in memory, so that they are stored encrypted on disk, and we don't. So we can provide additional security guarantees. So this smart card had to be retrieved, and there were two smart cards in the world, one in California and the other one in Australia, contained in safes in an office. The problem is that the engineer at this point was in the East Coast. So they contacted the colleague in Australia to get the smart card. The problem is that this engineer wanted to open the safe, but the combination for opening the safe was as you might imagine, in the password manager that was online. It was offline at the time. And luckily, the colleague in California had memorized the password for opening the safe, or like the combination to open the safe, and was able to get the smart card. So at this point, we had the smart card. We could insert it into the reader and restart the system. But the system failed with an error that said the password could not load any of the cards protecting this key. So at this point, the engineer in Australia decided to apply brute force and went to take power drills and open the safe, and got the other smart card, which unfortunately triggered the exact same error. After about 1 hour, the team realized that when they entered the smart card, they got a green light. But this didn't mean that the smart card actually worked correctly. It just meant that there was something that was inserted into the reader. So after some time, people realized that the card was entered the other way around, and we just they just flipped the card, and at this point, the service restarted and the outage ended, and the system was restored. So in this example system, we can see that reliability and security are crucial component. And I would argue that this is true for any trustworthy system. And it's very hard to build reliable and secure systems. And this is because, like, even though security and reliability has some common properties, we also need to design the system with taking into account these features, looking from different angles. And it's also easy to miss how these different requirements would interplay together. For example, in this case, like, we had a load balancing system, but the load balancing was not really well implemented because it didn't provide any load shedding. So when the first replica failed, even the secondary replica failed in the same way, which is not good. And the security measures that we had in place were like amplified the outage because they made the resolution of the outage harder. So yeah, let's see now what we should consider when designing a system that should be secure and reliable. So first of all, I think we should consider like what forces there are that could hinder the security that our system would like to offer. And these forces might be deliberate, for example, in the case of cyber criminals, or accidental, because maybe some people might, by mistake, leak user data. And so we want to perform usually a very careful risk analysis to first understand the motivations for the people that might be our adversaries, what they could be after and why, and what could be the targets that they are interested in, and what could happen in case they manage to be successful in their attack. So if we go, like, if you think back in the day, the first computer hackers were hobbyists, as I'm sure you know, and those were mostly motivated by knowing more, like improving their knowledge and even sometimes maybe showing off. And now this evolved very much, and we usually the hobbyists are evolved into professionals. So we have now vulnerability researchers, where that can be very good allies in making our system more secure. And usually they are motivated to make the system better. Then we might have other adversaries that can be financially motivated to maybe extract some information on, or maybe provide bad PR for the company. And also we need to consider accidental attackers, which could be insiders. For example, this could be employees that maybe can either be non-malicious. For example, they might make a mistake and accidentally expose some internal information that should be kept secret. Or maybe either they are compromised or they could be malicious and might want, for example, to retaliate against the company by injecting a backdoor in the source code, to maybe after they quit their job, still get access to production systems. And it's also very hard, I think, to understand the motives of specifically very strong adversaries. Like if we think about March 2016, we saw this a ransomware named Nokpatia, which was financially motivated. And yeah, it was like a regular ransomware where people would have to pay to get their files back. Otherwise, they would have their system unavailable. But just a year later, we also saw another piece of malware called Nokpatia, which initially looked like similar to Petya, also ransomware, probably also financially motivated. But later, it was quite clear that this was not like a regular ransomware, but it was more like a state-sponsored attack to basically undermine the stability of critical networks. So motivated attackers can actually act in very creative ways and try to hide their motives and identity. And we should keep this in mind when we do this kind of risk analysis. And I think focusing on the work of the attackers and how they act and what they do specifically is probably a better option instead of trying to find the motive. Let's see now some techniques that can help mitigate this risk, which can either be provided by insider or outsider attackers. So there are many design strategies for security that are applicable, but I would like to present a few that I think are not always considered in modern systems. So the first one is quite obvious, is least privilege, but I think especially now with cloud systems and so on, granting the fewest privileges necessary to perform the job to a task is not something that people always consider. Let's say, for example, in the case of a cloud project, reusing the same service account for multiple environments or multiple duties is actually an anti-pattern, and we should strive against this. And yeah, this I think it's probably obvious that people know about the principle of least privilege, but this is not always implemented properly in production. Another principle is zero trust. So as I spoke about before about Beyondcorp, we re-architected the corporate network in such a way that we don't give any trust to the network itself. We don't want any kind of implicit permissions that we give to users. It's not that if you come to if you come through a certain proxy or if you come through a certain network, but you're not authenticated or you don't have any other fine-grained protection measure, then you can access a system. We want every single access to be strongly encrypted and have strong authorization and authentication guarantees. Another design pattern that I think it's not always considered is multi-party authorization. And this is particularly important when we store very sensitive data. And as we look at many attacks that happen in this industry regarding breaches, what attackers are against, usually it's system administrators, because they have very strong powers. And it's very common that system administrators can unilaterally maybe have root access to a database. And this is a high risk, and we can mitigate it by having multi-party or at least two-party controls. If you think, for example, the nuclear missiles, we always have two keys where two people have to turn the key to actually start the attack. And I believe this should be something that we should consider more when we build secure systems. So we don't want anyone, ideally, in the company that can single-handedly access secret data or user data. Another important feature of our system should be that any access should be audited. And this makes us, in the case of an attack, we could go back, look at our logs, and see if people had a valid business reason for accessing this data. And we could, for example, ask any access to sensitive data to provide a justification to connect any access to a business reason to do that. And this is maybe also obvious, but I think it's not something that is implemented in many production systems. For example, it's common sometimes to have shared root accounts where multiple people have, let's say, a root password, and they could use this root account to do potential data exfiltration without any way to trace it back to the actual user that did the exfiltration, because all the actions appear to be done as root on the machine. Another aspect is recovery. So the ability to recover from a destructive action, it's very important. And preventing all breaches or destruction of data is very hard. But if we don't have a backup plan, then we are completely in the dark. And in this case, recovery can help us actually go back to the state where we were, at least before the attack. Security and reliability are distinct practices with a significant overlap in purpose. And we need both to build and maintain trustworthy systems. As we said before, a significant percentage of reliability issues are actually introduced by engineers that want just to push out new features to users, because our system is not just written once and we just deploy it and that's it. We are consistently working on that and improving it. And we want to, from an SRE point of view, we want to be able to balance the velocity in which we release new features and the reliability of the system. So how we do that is define SLOs. So SLOs are metrics, are based on metrics, and they are objective for these metrics to make sure that whenever we hit this objective, then our user is happy. This is, of course, a simplification. There are books, the entire books on the topic of SLOs, but I think this is a very condensed and nice two-line description. So if we meet our SLO, users are happy. If we don't, then users are unhappy because they cannot use our products in the way they want. But this still leaves us with some room for error. And we have an error budget, which allows us to make changes to the system and experience failures, but up to a limit so that the customer experience is not impacted. And finding good SLOs is very hard. And it's actually a large part of my job. And to give you an example, I will give you the example of Bigtable. Bigtable is a massively scaled distributed storage system for Google. And we have different kind of customers for Bigtable. One kind of customer is are services that depend on data from Bigtable for serving. And these services need very low latency and high availability. For example, you could think of a web page that needs data from Bigtable at the moment of rendering the page. Another case is another kind of users that need to run, for example, MapReduce jobs. or like some kind of batch analysis on a large amount of data. And in this case, what they care about is not really latency, but it's more throughput, because they want to analyze a lot of data in a short amount of time. So the properties that these two kind of users want from the system is very different. If we consider, for example, as a metric, the fullness of the request queue for Bigtable, if you want low latency, your request queue should be empty or almost empty all the time, so that your request will reach the server and will be answered in a very short time. Vice versa, if you perform a batch analysis, you want your queues to be full, or not empty, at least, so that you can actually optimize for throughput. And while your system is idle doing some stuff, then Bigtable will have work to do to process your data. So in this case, success and failure are antithetical for this kind of set of users. So defining an SLO is very hard. What Google ended up doing was to actually partition the infrastructure in two flavors of Bigtable. One kind of data centers had Bigtable in a flavor that provided low latency, but was not good for throughput. And other data centers offered Bigtable in a flavor that provided good performance for throughput, but not like bad performance for latency. So in this case, the engineers were able to define two separate SLOs and treat the two different user bases as two different systems. And this basically was a compromise between what user needed and cost. Because in this way, we can save on cost, because making a single system that actually satisfied both requirements would be very expensive, while splitting the system in two can be maybe more costly from a maintenance point of view, but it's definitely cheaper for the design, implementation, and giving all these guarantees. So before we talked about design strategy for security, I would like to argue that many of those strategies, or actually all of them, are actually applicable also for reliability. We talked before about least privilege, and this is also very important from a reliability perspective. If we, for example, use the same role to run different workloads, then it's very hard to have isolation between these different workloads. And while instead, if we give to every role that runs a job only the permissions that it needs, it's much easier to isolate the workloads and also provide safety against bugs. So if a user has permission to change, let's say, only a set of jobs and doesn't have permission to change another set of jobs, then it's very unlikely that this engineer or maybe automation that would do the releases could actually cause harm to the other job because they don't have permission to touch it. So in this case, the principle of least privilege, I would argue, is very important, also not only for security, but also for reliability. Before we talked about zero trust, and zero touch is sort of related. With zero trust, we force users, or at least human access, to go through enforcement points where we check that they actually have permissions to do a certain action, and we don't allow certain operations just based on, for example, the network where a user is coming from. And zero touch is kind of similar. So we argue that changes to production should not be done manually, but should go through automation. And this would allow humans to first not do any, for example, mistyping of a command, because the automation would do the operation, not the human itself. So the operation would be represented in an algorithm that maybe went through code review and was vetted. So it's much less likely to actually do a manual mistake because we have the tooling that does the change. And also, automation makes changes much more predictable and controlled. For example, we could have automation that rate limits the amount of changes that we can do to a system. Let's say we only update one data center at a time, and we wait between the update of different data centers. So we do a slow rollout, and this cannot be overridden unless it's an emergency. And this would enforce that every release would go through the same process. And also, this would allow to have better auditing and detection. For multi-party authorization, as we said before, we have the idea is to have two people to approve a certain operation. And this is very important in terms of security, but also in terms of reliability. So we can have a second pair of eyes that can look on an operation and decide if this is actually a sensible and risk-free or low-risk operation. And we can prevent unintentional mistakes. The other point is auditing and detection. So having actually good logging and good detection of what happened is it's fundamental, I would say, for handling an outage and understanding how to fix the system in the case when we have an incident. And so it's not only very important for forensic analysis of aftermath of an attack, but also for an outage. And it's very important to be able to actually respond to the incident. Also, kind of related to this, for reliability, we usually have auditing of resource consumption, and this allows us to have good monitoring and alerting. Recovery, I think it's quite obvious for the reliability of our service. If our service is down, we want to be able to recover it. It's related to having backups and testing them and so on. To give you a concrete example, recently some colleagues of mine open sourced a project called GLOME, which stands for Generic Low Overhead Message Exchange, which is available on GitHub. It's not an official Google product, but I think it's a very interesting concept, at least. The idea is to limit basically remove the need of root passwords on servers. And we do this by, instead of allowing users to log in with a root password and then be able to perform any operation, there is a challenge response system where a user can log in and then use authenticate with a key to get access to the system. So I would argue that we need to shift security and reliability at the beginning of the life cycle of our system. We need to consider security and reliability properties at the beginning of the design, during the design phase of a system. And because those are two fundamental properties that we cannot just build in at the end of the process. And this is very fundamental in the case of many systems that we have now that are connected to the internet and store user data. I would argue that it's not really possible to build a system that is fundamentally secure without being also reliable. And there are very few use cases where you want security without reliability. And yeah, we need to work on leadership and so on to have these two properties built in the system from the beginning, the design phase. So this talk was inspired by the work of many people that went into these 3 books. The latest one is Building Secure and Reliable Systems, and was published in March this year, and it's available on the Google SRE page, and it's edited. All the three books are edited by O'Reilly, so you can also find them on the O'Reilly website or on any store that sells O'Reilly books. So the Site Reliability Engineering one was the first book that was published. I believe this is also available online. And the first book kind of talks about the design principles of SRE in a more like, I wouldn't say philosophical way, but more like theoretical way. The Site Reliability Workbook is more with a practical approach. And the latest one is also considering not only reliability, but security. So yeah, that's all I had. You can contact me at this contact points if you wish. And that's all. Thank you.
Ok, grazie Federico, io ritorno all'italiano per il tuo intervento, perfettamente in tempo, estremamente interessante, però switch un attimo in inglese perché c'è una domanda per te che è in inglese e quindi te la faccio in inglese. Ci scrivono dicendo a proposito di multi-party authorization, is it always a custom implementation in your experience? Are there any free or open source tools that can be used to implement the approval rule functionality?
So I'm not aware of open source implementation. I think we should work more on this aspect. I believe, so I didn't look that much into Gloam, which is this project that was open sourced recently. But I believe it has at least the protocol could support multi-party authorization. But yeah, I think it's not something that we see often in practice in the industry, and definitely we would need some open source implementation. I think it would be a very good addition to the free tools that we have.
Ok, grazie, non ci sono altre domande. Io ce ne avrei 162.000, ma lasciamo alla prossima volta. In particolare al concetto di affidabilità dei sistemi di sistemi e l'effetto domino, ma insomma veramente potrebbe essere oggetto di un altro talk. Grazie ancora.